Hey guys, we're senior mechanical engineering students at Clemson University, and we were tasked with making your lunar rover. Hopefully you'll find this video educational and it'll help you in your curriculum. My name is Amal Kumthakar.
My name is Keith Page and I was in charge of mining.
My name is Stephen Fonmiller and I did the chassis design.
My name is Richard Walter and I was in charge of the control system.
My name is Chandler Satterfield and I was in charge of the powertrain. When designing our rover, one of the main objectives was to make sure that it was a learning experience for 5th grade students. When studying the 5th grade curriculum in South Carolina, we found out that one of the main focal points is the study of forces in motion. We're going to dig a little bit deeper into the functionality of our rover with respect to speed. The first section of our rover we're going to cover is speed, which is related to the motion portion of your curriculum. But in order to understand speed, it's important to understand how the geometry of a circle relates to the distance traveled by a rover. So, the main part of a circle is the diameter. The diameter is the distance from one side to the other, crossing the middle point. 1/2 of this is the radius, which travels from the middle point to one side. Mathematically, this can be calculated as diameter divided by 2 equals radius. Now, we can relate this radius to the distance around the circle called the circumference. And this equation is circumference equals 2 times pi times radius. Now, we have to figure out what this circumference about the circle means to how far it travels.
Now that Chandler has shown you guys how to calculate the circumference of a circle, we've come outside so we'd have enough room to use this bike tire to show you how the circumference of a circle relates to its linear motion. Remember how to calculate the circumference of a circle? First you have to get the diameter, which is the distance from one edge of the circle to the other, crossing through the center point. In this case, our radius, or our diameter, is going to be 26.5 inches, and the radius will be half of that. So we take 26.5 inches, divide that by 2, and we get our radius of 13.25. And then from the radius, you remember how to calculate the circumference of a circle? That'll be 2 pi times the radius. And for this wheel, our circumference is going to be 83.25 inches. We've put this black piece of tape here so you can mark this point on the circle, and we're going to show you how the circumference of the circle relates to its linear motion here. So starting at the beginning of this measuring tape, we're just going to roll along. And here you can see that we came to 83.5 inches, which is almost exactly what we calculated.
Now that we have related the circumference of a circle to the distance it travels, we're going to take a look at what our rover wheel actually looks like. Our rover wheel is a circle with square-shaped spokes all the way around it to create extra traction. For our purposes, we're going to assume the ground comes all the way up to the circle so we don't have to take into account the square spokes as it relates to speed. So, if you look at the picture inserted into the video, you're going to see that the diameter of this part of the circle, which is the distance all the way across, is 1.5 inches. In order to get this to radius, remember, we need to figure out what the diameter, or the radius is. So, we need to figure out what this distance is. If you remember, diameter divided by 2 equals our radius. So, 1.5 divided by 2 equals radius, which equals 0.75, and in fraction form, 3/4. Now, we can relate our circumference equation, which is C equals 2 pi r, to a radius to figure out what the circumference of the circle is. So, circumference of the circle equals 2 times pi times our radius of 3/4. If you cancel these, we can see that C equals 3 pi over 2, which is approximately 4.71 inches. Now that we know the circumference of our wheel is 4.71 inches, we can think back to the bike tire example, that every time the tire rotates, it travels one circumference. So the linear distance of travel for this wheel, distance, is 4.71 inches per rotation. Now, we mounted a motor to turn this wheel right in the center of the wheel, and that motor is rated for 200 RPMs. Motor equals 200 RPMs. RPM stands for rotations per minute. So this motor is essentially spinning at a rate that it is going 200 rotations per minute and making the wheel go that fast as well. So we can say that every time this motor rotates 4.71 inches and it's rotating 200 times in a minute, we can multiply these two together and say 4.71 inches per rotation times 200 rotations per minute will get you your linear velocity, which is about 942 inches per minute. Now, engineers don't really use inches per minute. We do, however, use feet per second. So in feet per second, this is about 1.3.
Hey guys, so I hope this video was helpful. Again, we didn't use the values that our rover actually weigh or how much the regolith weighs. We did just simple numbers to simplify the calculations. If you want to do the calculations and get more accurate values to what the rover actually does, you can use the rover in the kit that we provided and follow this process, but with the real numbers that you guys measure or weigh or anything else to get a more accurate representation of how our rover acts.
As long as we tie it down onto the adapter,
Works too well.
You can take this.
Ooh.